Now let's talk about inference. You remember that correlation is just a statistic. It's statistics of your sample. And if you see, for example, a strong correlation in your sample, does it mean that the correlation will be same strong for your population? Okay. And the inference, the approach in this case will be similar that we have used for the variance, that we have used for the average values or for the proportion, meaning that we need to know the sampling distribution for the correlation coefficient. And then we use the sampling distribution to calculate confidence intervals or to make a test, for example, if correlation is equal to 0 or it's, for example, it does not exceed or at least equal to a particular value. Okay, I'll show you only how to calculate confidence intervals because I think that you already know how to get the p-value if you know the distribution. Okay, and well, first of all, again, we are talking about population and the sample. For the sample, you already know that if you have a sample, the correlation, we denote correlation by using the letter R, the Latin letter R. For the population, we will use rho. Okay, so it's a Greek letter that corresponds to R in Latin. So what we need to know is, so for the given row, and for the given sample size n, what will be the distribution of R values? So how far the R values can go from the real one from the row for the given sample. Okay, so let's discuss that. Let's start with some simulations which I made in R, and I started with population where the rho, the true correlation coefficient, is 0.96, so it's pretty high. Okay, so if we take a sample size of 5 and repeat it many times, so if we take a lot of samples of size 5 from this population, that will be the distribution of the correlation coefficient. So the red line, it's a true correlation, and you see indeed that most of the time the correlation coefficients are around true, right? So it can be either above true or below true. And then sometimes it can be quite low. For example, I got some values with the correlation was about 0.65. So if the sample size is 5 and the correlation coefficient is large, you still have a quite big spread of the coefficient. That's one thing. The second thing, it doesn't look normal, right? It doesn't look as any of the distributions we know, and that's a bad thing, but that's a bad sign actually. Let's see if we increase the sample size. In this case, I have sample size 10. The shape of distribution is the same. We still have this left skewed distribution, right? But now the spread of the correlation coefficients for our samples is more narrow. So you can see that indeed we have somewhere between 0.8 and 1. But the true correlation coefficient is 0.96. You can also see that the spread is not symmetric about the true correlation coefficient if you look at only at the range of the spread, right? Then the correlation is 30. Again, the shape is more or less the same, but now the spread is smaller. So we have 0.9 and 1. Then if sample size is 100, it looks very even symmetric. I think it looks even almost as a normally distributed values. But it's very rarely we have sample size 100, right? So what to do in this case? Then if you look at this case with sample size 100, you can see that the spread is quite narrow. So we have the same as for the other statistics, right? So if the sample size is large, then the statistics, the uncertainty of statistics is small. Okay, so the statistics of your sample is very close to the population parameter. But the problem is that very too often we can work only with the small samples, right? Now let's take another example. In this case, my correlation is moderate correlation. So I have 0.57 for the population. Let's see if we repeat the same things again. So if we take different samples of different size, what happened to the correlation? Okay. So let's take the first one, and you can see that the spread is huge. Even though the true correlation coefficient is 0.57, the spread is between -1 and +1. Yes, the most of the cases it's here, you can see, but still you may have a sample with a negative correlation even though the population has a moderate positive correlation. If sample size is 10, luckily in this case we don't have -1, but we still have like up to -0.5. Yeah, most of the values are positive. That's a good sign, of course. But still, for the sample size 10 and the moderate correlation in the population, the spread of the correlation coefficient is huge. So it's very important that you calculate the confidence intervals and make a test for the correlation coefficient, especially if the value for a sample is relatively small. Okay. Then the same for 30, things are getting a little bit better. Still, the spread is bigger than we had before, but now we don't have any negative values. And then for the sample size 100, we have some only positive values as well. And you can see that the most of the values are distributed around the true. Okay. So if you look at again, if you zoom in, you can see that even though the true correlation is about 0.6, we got some about 0.3 here, and we got also about 0.7, 0.75 here. Okay. So what we can conclude from these examples? We can conclude the following. First of all, the bigger sample size, the more symmetric distribution is, and it looks close to normal, but for the small sample size, it's skewed. Okay. Then the bigger sample size and the smaller uncertainties, that's what we expected already. And also the spread, the uncertainty of the correlation for your samples depends on the correlation coefficient for your population. Okay, so the larger correlation between two variables, the smaller uncertainty. Okay, so that's what we know. The problem is the distribution of the correlation coefficient. It doesn't look similar to any of the theoretical distributions we know. And indeed, the correlation doesn't have any theoretical distribution. However, a very famous statistician, Robert Fisher, found out that if the population distribution of x and y variables are close to normal, so it means that if you look at the x and y separately, make a normality test, and it seems like they were taken from normally distributed population, if they are random, that's very important, and all statistics samples should be taken randomly. And if sample size is large enough, in this case, you need at least 10 values. You need at least 10 objects, sorry. So it means that 10 values for x and 10 values for y. But in this case, you can calculate a statistic. I will call it z prime, this one. Okay, this is how to calculate it. You take the correlation coefficient for your sample, add 1, then take 1 minus correlation coefficient, take a ratio, and then use this logarithm, the natural logarithm, and multiply to 0.5. Okay, then this statistic z prime will be distributed almost normally with the standard deviation, where n is a sample size. Okay. So that gives us a sort of hope how to calculate the confidence intervals. We cannot do it directly for R. So first we use R to calculate Z prime. Okay. So we sort of, instead of R, we will calculate confidence intervals for these Z prime statistics. And then we can recalculate it back, because for any function there is always, we can always find an inverse function. Okay. Sounds a bit maybe tricky, but let me show you some more detailed examples and some calculations. Okay.